Hi, I'm Jox and welcome to Layman's Guide to Cracking the Coding Interview. So before we solve merge sort and we solved the quick sort whose runtime was O of n log n, and now we're going to be doing for the heap sort, and the runtime for the heap sort is also O of n log n. However, this is slightly slower than the previous two. So however, this data structure is really important for the binary tree data structures. So let's begin. So there are two kinds of a heap. One is a min heap, another is a max heap. So if you use a max heap, we get the sorting from ascending order, but if you use a min heap, we'll get the sorting from the descending order. So we're gonna use a min heap so that we're gonna be seeing the sorting in the form of descending order. So it's gonna be 9, 8, 7, 6, 5, 4, 3, 2, 1. That would be a sorting case. So today we're gonna be using the min heap, but most popular is a max heap. And there are tons of resources that you could explore to find out which heaps are better to implement. So just for me, for this case, I'm going to be using the min heap. And the heap have a following property. So heap, the pixels that we are seeing on the left hand side is a full and complete binary tree, and the one on the right hand side is a complete, and those two satisfy the conditions for the heap. And the other property is the parent. So if you wanted to find the parent node from the given tree, we have these equations: the floor value of index by 2. So if this is the index, this would be the parent using these equations. And if you want to find the child, then this is the equations. So twice of index plus 1 and twice of index plus 2. We will have a 2 childs because every node have a left and the right nodes. So in this case, if it's 0, then 1 and 2 would be the child. So this would be the 0, 0, so 1 and 2. So which satisfy the property. So there are two types of a tree, and there's one more tree which doesn't satisfy the property of heap. It's this one, the one that doesn't, which is not complete, doesn't satisfy the property of heap. To get the details of the property of the heap, you can follow some of the resources. I'll give you the link below after this video. So any tree that doesn't have a left node but that has a right node doesn't satisfy the heap property. So heap, we can do two things for the heap. One is the addition of a heap, another is the deletion of heap. Every time after we delete the items from the heap, then we will have a sorted array. So usually we don't need to perform the additions of heap, but just for the sake of simplicity and for us to understand more in detail, I'm gonna do the addition of heap. Addition of heap would simply will have this thing. So let's do. So at first we add 4 to the heap. So this is the root node, and every time when we add another item, it should start from the left, and every time we do, we compare, is the parent item smaller than the last item. So in this case, we are doing a min heap, so min should be on the as a root and the max should be at the bottom. So in this case, 4 is still smaller, so we don't do any swapping. So we add 3 here. So since 3 is smaller than 4, so we need to do swapping, and this is also called bubble up. So when we do any additions, if the we compare always with the parent and to the added node. So in that case, we always do the bubble up, so that the smaller item or the node gonna go at the top, and the bigger item or the node gonna go at the bottom, that is left or right. So we have 3 items that's been added. Now let's add 6. First it's been sorted, and then we add 6. So we compare. We always check this property. So once we hit this, we start adding again. So right now it's true, it's satisfied, we don't have to do anything. Then we add 5, it's also okay. And we add 8, that's also fine. So when we add 2, so 2 is the smaller than its parent node, so we do the swapping. So we not just do the swapping with one parent, we do with the complete entire. That's why we call it bubble up approach. So we did the swapping, and then we compare with 3 as well. Now 2 gonna go up, 3 gonna go at the bottom. So here we go. So now it satisfies the heap property, the min heap. Now we add 1. So 1 is the smallest. So we need to swap here, swap here, swap here. It keeps continuing, going from the bottom to up. So 6 down, 4 up. And 1 gonna go as a parent and 5 gonna be as a root node. So here we go. Now this has been sorted. Sorted in a sense, this is a min heap. So we have all the items been added. So let's write the code. Since this video might take longer, so I have already implemented that. I'm just gonna show the quick code and I'm gonna run later. So this is just for the addition. So we have a heap as a class, and I already defined here. I'll show you this in a moment. So first we do the addition, right? So we have a heap. Heap have a method called add node. So we're adding the node. Once we add the node, it should be like this. So I'll show you while I do the debug later. I'll run the program a little later, but first let me show you the class of the heap. So we have a node list and we have a positions. At first, when there is no item, it's -1. So every time the first item would be the 0th position. So that's why we have a -1 at the beginning. So every time we add, we do the +1 for the last positions, and we add that node on the node list. So we have it here. We append the node and then we increment and we do the bubble up. So at first we don't have to perform any bubble node because it's always on the top and there's no any items to compare with. So we keep on adding, and then we have to do bubble up, just like we saw it right over here. When we add the 1 at the last, it does a bubble up because we're comparing with the parent until we hit to the end. So that's why I have a bubble node. We can do it in a recursive way as well as an iterative way. You can choose which one you like. So we have a base case, index equals to 0. That means have we reached to the root node, or have we reached to the last top index? Yes. In that case, we just return true. If not, then we do the comparison. So every time we do the comparison, we do the swapping. This is the recursive way, and this is the iterative way. So you can choose whichever you like. So we have a parent as a math.floor. And that's why I have imported the library math right on the top. And we have a parent node, index of the parent node, and then we compare, we do the swapping based on the conditions. Because we're using the min heap, we are using this sign. If the parent node is greater than the current index. So in this case, we have that. So let's get back. And we need to do the deletions because for the heap, we have a two method. One is the add node, another is the delete. I'll come to the delete just in a moment. Let me close this. So right now it's not sorted. It's just we have a property. It's a min heap. So now we need to do deletions in order to have a sorted array. So we don't put this as a runtime. Even if you put this, it's just the ONF time. So we need to do the deletions. Earlier we talked about the bubble up because we're comparing parent node. Now when we do the deletions, it will do the bubble down because we're comparing with the child node. So okay, let's do deletion. So first, whenever we delete, we always delete the root node so that the root goes at the last node, because we don't want to delete the array. So we just put the last index or the index as a pointer where we make sure that we're not going to comparing anything below this or anything on the right hand side of the index. So first we delete the root as 1, and then once we delete the root, we have to swap this. So 6 would be act as a root and the 1 would be deleted. And when you do that, we put the index here so that we're never going to count anything below this. So once 1 is at the bottom, we compare with the rest of the child node. So the child for the 6 would be 2 and 3. So whichever is the smallest, we pick that one. So we swap that. So this approach is called bubble down. So because we are comparing with first level And second level, if we have more levels, we'll be comparing with all other levels. So it's almost like a bubble down approach. So since we did the swapping, again we need to compare with its child. So here the 6 is bigger than 5, so we do the swapping. So while we do the swapping, you can see it here. I'm sorting this thing, whatever happens here. So now we are deleting the 2. Sorry, we have a 2 and we are deleting the 2, and then we have to swap with the 4. So we delete 2, we swap with the 4. We always swap with the last index in the tree. So now we have a 2 here, so anything on the right hand side, we don't do anything. Anything that is above is our current node or the current tree. So now the bubble down, 3, we compare 3 and 4, so 3 is smaller, that goes up. So we have it here, so 3 at the top, and we swap with the 4. So we delete the 3 again, and whenever we delete, we always swap with the last node. Since 1 and 2 is not counted, so we don't play with this node, we just keep it as an isolated node. So we did the swapping, now we do the bubble down approach. So 4 is smaller than 8, so it goes down, that goes up. It's done here. Now again we do the deletions. So when we delete, we compare with the 5. And then we swap. So at this point, exactly at this point, like node 5 is by default in the right order. So we don't need to do any bubble down. That happens sometimes. So in that situation, we just leave it as it is. So now we are deleting 5. So once we delete 5, the last index right now would be 6, because we have an index here which we don't count. So we do the swapping. So 5 over here, 6 goes to the top. And we do this bubble down. So now we want to delete 5 because we have a 2 5, so still there's one more 5, we need to delete that. Usually we swap with the last index, so we just have a remaining of 3 items on the array. So we swap, so now we only have a 2, and finally we do the swapping, bubble down. This 6 gonna go up, 8 gonna go down, and once we are almost at the end, now it's almost completed. So by now the tree is sorted. You can see it here, 8 6 5 5 4 3 2 1. It's sorted. As I mentioned, in a min heap the order would be a descending order, and in a max heap it would be an ascending order. So let's run the program. So earlier we did the additions, now we're doing the deletions, and this is the code for the deletes. This is the function for the deletions, and at first we do the swapping with the root index with the last one, and after that we need to do the bubble down. So let me just get the bubble down code. I'm just copying it right here. Rather I'll show you and run the program right in my IDE. So okay, we have this given one, and I'm doing some addition. So let's see when we do the addition what's gonna be our case. I'm just gonna put the breakpoints. Let me run first. Okay, so we do have it. Then I'm gonna do the debug. So every time we do the addition, it will always check. So let me go to the heap and let's see the node list. Actually, I'm doing the deletions. Let me just come here and then debug again. All right, so when we add 4 5 3 6 so on, this is the node. In the heap we have a node list in this order. That's 1 is bigger than 2 and 5, and 2 is bigger than 2 is smaller than 3 and 5, and 5 is smaller than 8 and 6, and the 4 let me show you in the pictures again. That would be much clear. Before we do the deletions, let me reach to the addition. Okay, it's hold on, not even here. Okay, right here. So we see the tree structure, and this is our node list in the tree. So this is a parent, this one have a 2 child, and this is the parent, this one have a 2 child, and this one have a 2 child. So 1 2 3 4 5 6 7 8, we have 8. So this is the case, 1 2 3 4 5 6 7 8. So this is the case. So now let's do the deletion so that we could get the in a sorted order. So once I delete, the 1's gonna go here, 2 is gonna come at the top. So this was already done, a bubble down approach. So anything below the last index we're not gonna count, as I mentioned earlier. So now last index is at over here, the second last items, right? So now we have a 3, the smallest one, because it's a min heap every time. So we're gonna delete that as well. It does all the bubble down sorting. And 4 5 5 6 and 8, one more. So here we go, we have 8 6 5 5 4 3 2 1. So that's the order that we have. So the runtime for this would be also n of log n, so big O of n log n. But however, this is slightly slower because we have to perform bubble down approach and the bubble down approach every time, not the bubble up, because that's the addition. We don't count for the addition. So because of this thing, it's slightly slower despite having the n of log n runtime. So thank you.